All right, good morning, everyone. So yesterday we started talking about entropy. So again, entropy is a measure of a system's disorder. So meaning that typically when a system is irreversible, what it does is it seeks a state of higher disorder, means it has to increase its entropy. However, a system which is reversible, meaning it has as much probability going forward as backwards, and then has to have a change in entropy which is equal to 0. So for an isothermal process, we define then that the change in entropy was equal to the heat divided by the temperature, where the temperature here is constant. Or if it has a non-constant temperature, then it's equal to the integral of the heat which is flowing into the system divided by the temperature. So again, here we have to know what kind of process it actually is to know what this guy is, right? So to know how dq depends on the temperature. And finally, this brings us to the second law of thermodynamics, which says that the change in entropy must be greater than or equal to 0 for an entire system. It can never actually be negative. So let's do an example. See how this actually works. So here I have 1 mole of a monatomic ideal gas, which goes through this cycle here. So this thing starts out in state A, goes then to state B, goes to state C, and then comes back to state A. So here we know it starts off at initial pressure with initial volume. Then stays at the same pressure, goes to a volume which is 4 times the initial volume, and then changes its pressure to twice the initial pressure, and then goes back to the original state. Okay, so this is a cyclic process. So here what we want to do then is find what is the work divided by the initial pressure divided by the initial volume when this thing goes from state A to state C along this particular path here. So this is going from A to C along the path ABC. Okay. Then we want to know what is the change in internal energy per initial pressure per initial volume going from B to C. And then we also want to know what is the change in internal energy for the entire cycle. And then what's the change in entropy for going from B to C. And then finally, what's the change in entropy for the entire cycle. So let's do that. So let's look at the first part first. So what type of process is our system going through going from A to B? Is this an adiabatic? Is this an isothermal? Is this an isobolometric? Is this an isobaric? What kind of process would this be going from A to B?
So we have isobolometric.
Almost. That's going from B to C.
Very
Going from A to B. Well, I'll come back to you for B to C. So what kind of process is that? So it has constant pressure, right? So which process has constant pressure? Isobaric, right? So going from A to B, we know that this thing does have a isobaric, okay? And then going from B to C, Teddy, what kind of process is that? Isobolometric. Good. So we want to know how much work is done going from here to here, up to here to here. But since this is isobolometric, how much work is done going from B to C? 0, right? So anytime I have an isobolometric, this has to have 0 work, which means the entire work going from A to C is simply the amount of work which is going from A to B, since there is no work going from B to C. So in this case, then we know that what? The work going from A to C is simply equal to the work done going from A to B, plus then the work done going from B to C, but the work done from B to C is simply equal to 0 because this is isobolometric. So good. We also know that what? Work on a PV diagram is simply the area under the curve for an isobaric, which means that the work going from A to B is simply the amount of work contained inside of this rectangle here, which means that this is going to be equal to what? The area contained in A to B. So here the area then is going to be the base times the height. So in this case, the height is simply the initial pressure, P0 times the base. The base then is equal to the change in volume. So this is going to be equal to P0 times the change of volume, which is V1 minus the initial. So this is going to be equal to what? 3 times P initial times the initial. Because here I know that the final volume is 4 times the size of the original volume. So I get 4 times, or 4 minus 1, which is 3. So finally, put it in the form that we want. In this case, it says that the work per initial volume per initial pressure is then simply equal to 3. So this ratio is equal to 3. All right. For part B, we now want to know what is the change in internal energy per initial pressure per initial volume going from B to C. But again, Teddy already told us that going from B to C, we have what kind of process? Isovolumetric. And what we know is that for an isovolumetric, our change in internal energy is simply equal to the number of moles times the molar specific heat at constant volume times then the change in temperature. Okay. Now, what else do we know? We know this has 1 mole. We know this is a monatomic gas, which means that our CV is simply equal to 3/2 times the universal gas constant, since this is a monatomic gas. What else do we know? Well, we also then have to find a relationship to the change in temperature. So how about we find the change in temperature?
Ideal gas law.
Ideal gas law, very good. So in this case, we know that what? This thing has to satisfy the ideal gas law, which means that at the initial point, I have to have that the initial pressure times the initial volume must then be equal to the number of moles times the universal gas constant times the initial temperature. And then I also know that it has to satisfy the ideal gas law at the final state as well, which means that the final pressure times the final volume must be equal to the number of moles times universal gas constant times then the temperature. Good. So if I solve each one of these for the temperature, this tells me then that my change in temperature, which is then going to be equal to the final temperature minus the initial temperature, is then going to be equal to what? The final pressure times the final volume divided by the number of moles times the universal gas constant minus the initial pressure times the initial volume divided by the number of moles times the universal gas constant. This is my change in temperature. Good. From here, we also know that this is 4 times the initial. This is twice the initial. This is 4 times the initial. So this is like 8 times the initial. Minus the initial, which is the same thing then as 7. So this is going to be 7 times the initial volume times the initial pressure, all divided by the number of moles times the universal gas constant. Assuming I did that properly. Was okay? Good. So finally, we can put everything together. So let's put everything together. So this finally tells me then that, and then I change it internal energy then, going from B to C, is then equal to 1 mole times 3/2 times R times my change in temperature. Actually, this line is 10. So times my change in temperature, which is then equal to 7 times the initial volume times the initial pressure divided by the number of moles times the universal gas constant. Good. So the number of moles are going to cancel out. Universal gas constant cancel out. So it's going to be the same thing then as what? 21/2 times the initial pressure times the initial volume. Finally, put it in this state. We finally then have that the change in internal energy going from A to B, or sorry, B to C, divided by the initial pressure times the initial volume, that is equal to 21/2. Okay? For state C, or question C, then says for the entire cycle. So here I'm starting off at A. I go around all the way back to A, but what is the initial temperature at A? The initial temperature. What's the final temperature at A? The initial temperature, which means my change in temperature is how much? 0, which means that my change in internal energy then must be equal to 0. Nice and easy. Okay. So as long as it's cyclic, my change in internal energy must be equal to 0, because I start and finish at the same final state. So in this case, I know my change in temperature is equal to the initial temperature minus the initial temperature, which is simply equal to 0. Okay. So finally, let's deal with this guy. For part D, we now want to know what is the change in entropy. So good. So let's first talk about, again, what type of process is this? This is an isovolumetric process. Teddy already told us that that means the work is equal to 0, which means by the first law of thermodynamics, the change in internal energy then must simply be equal to the heat. Good. And we also know the change in internal energy by what we already did is simply over here. This is the number of moles times the universal gas constant times the change in temperature must then be equal to the heat. So what this means then is that this is a case where the temperature is not equal to a constant, which means to find a change in entropy, we're going to have to do that integral. Now, to do that integral, we have to figure out what dq is. To find dq, we're simply going to consider an infinitesimal change of the heat, which means we're going to look at just a differential of this entire thing. So if I look at a differential, number of moles stays fixed. This is simply a constant. The temperature is changing by a differential amount, while the heat is changing by a differential amount. So this means if I look at a differential of this is the number of moles times the molar specific heat at constant volume times the differential change in temperature must then be equal to the differential heat. So this then says that our change in entropy going then from states B to C is equal to the differential heat divided by the actual temperature. But my differential heat is simply related to my differential temperature this way. So all I'm going to do is I'm going to replace dq here with this, and then do an integral with respect to temperature instead. Okay with this? So let's do that. So finally, plugging that in, we then get that the change in entropy is going to be equal to the number of moles times the molar specific heat at constant volume times the integral from the temperature at B to the temperature at C times then dq, which is then going to be dt, divided then by the temperature. What's the integral of dt over t?
Natural log t.
Good. So this is natural over t. So finally, this is going to become number of moles times the number of or molar specific heat at constant volume times the natural log then of the temperature at C divided by the temperature at B. Now from here, we just need to know what's the temperature at C and what's the temperature at B. So to do that, we can then again use the ideal gas laws. So again, what we know is that what the pressure at C times the volume at C must be equal to the number of moles times the universal gas constant times the temperature at C. But we also have to have the pressure at B times the volume at B must be equal to the number of moles times the universal gas constant times the temperature at B, which means if I take a ratio of these two, simply divide them, we then get a ratio of the two temperatures. So let's do that. So finally, we then get that the pressure at C times the volume at C divided by the pressure at B times the volume at B must then be equal to the temperature of C divided by the temperature of B. Well, we also know that the pressure at C is twice the size of the pressure at B, but the volume at C is exactly the same as the volume at B because it's not a volumetric process, which means this is the same as this, but this guy is twice the size of this, which means this ratio is simply equal to 2. Okay. Finally, we can plug in our numbers. Here it is. This is then going to be equal to what? NCV times the natural log of 2. So this is going to be equal to 1 mole times 3 halves times R times the natural log of 2. Plug in my numbers. What I find in this case then is my change in entropy going from B to C is 0.864 joules per Kelvin. So this is my change in entropy. Okay. Finally, for part E, we want to know what is the change in entropy for the entire system. Well, again, we know that Q is not constant, which means we still have to do this integral, but we already know the result of this integral, that's simply this guy. So in this case, for part E, the change in entropy for the cycle then is going to be equal to the number of moles times the molar specific heat at constant volume times the natural log of the ratio of the temperature at A to the temperature at A. Right? Because it starts off at A and then comes back to A. Well, what's the temperature at A divided by the temperature at A? 1, and what's the natural log of 1? 0. So for any cycle, at least for a reversible process, my change in entropy then has to be equal to 0. So that tells me here that this is actually a reversible process. This cycle that we run it through. It's okay? So next thing we want to look at is, this worked because we had a constant volume. But what happens if we don't have a constant volume? How do we then calculate the change in entropy when we don't have a constant volume? How do we calculate the entropy in there? So for our case, again, we're going to be mostly just interested in ideal gas. So let's talk about the ideal gas. So we know that, again, the change in entropy is equal to the integral from the initial state, which we're going to call A, to the final state of B. And this is going to be equal to the differential change in heat divided by the temperature. Now, in this case, since we're considering an ideal gas, what do we know? So we know that the change in internal energy by the first law of thermodynamics must be equal to the differential change in heat minus the differential work done by the gas. We use this definition instead. Now, this guy I can add to the other side. So this tells me that the differential heat then is going to be equal to the differential change in internal energy plus then the differential work done by the gas. Now, we also know that the work done by the gas is simply equal to the integral of the pressure integrated over the volume, but since I'm looking at the differential work, that means I take a derivative of that, which means it's just going to be the integrand, which is then pressure times the differential volume. So it's the same thing then as the differential internal energy plus the pressure times the differential volume. This guy we can always rewrite as N times CV times dt plus then the pressure times the differential volume. Okay? So let's use that over here. So finally, I can write this then as the integral from A to B of dq, but dq is going to be all this fun stuff. So let's do that. Actually, let me do it in stages. So next thing we want to do is consider this guy divided by the temperature. So let's look at that. So now I want to look at dq divided by t, because this is the integrand at which I want to integrate. So if I plug that in, that's going to be equal then to n times cv times dt divided by t plus the pressure divided by the temperature times dV. But here, I can rewrite the pressure divided by the temperature, again, using my ideal gas law. So let's use our ideal gas law. So from here, we know that, again, pressure times the volume is equal to the number of moles times universal gas constant times the temperature, which means that the pressure divided by the temperature is also equal to the number of moles times the universal gas constant divided by the volume. Okay with this? So let's plug that in here. So finally, this thing is going to become the number of moles times Cv times the differential temperature divided by the temperature plus the number of moles times the universal gas constant times the differential volume divided by the volume. Let's take those two results and plug them in here. So finally, this is going to become the number of moles times the specific heat at constant volume times the integral then of the temperature from the initial temperature, which is the temperature at A, to the final temperature at B, plus the number of moles times the universal gas constant times the integral of the volume divided by the volume from the initial volume to the final volume. I'm going to integrate this guy from the volume at A to the volume at B. Okay. Finally, we just want to integrate this. Teddy already told us that the integral of dt over t is a natural log. The integral of dv over d then is also a natural log. So finally, putting all these things together, we finally then say that the most general way to write the change in entropy for an ideal gas then is equal to the number of moles times the molar specific heat at constant volume times the natural log of the ratio of the temperature at the final temperature divided by the initial temperature, plus the number of moles times the universal gas constant times the natural log of the final area divided by the initial area. Ooh. That was a lot of work to get there. So this one says is that through any type of thermodynamic process that we could do with a ideal gas, this is the way we would calculate the change in entropy. So this takes into account the fact that the temperature can be changing as well as the volume can be changing as well. And the pressure. So this is going to be true for any type of thermodynamic process. So any one of those thermodynamic processes we looked at, the isobolometric, the isobaric, the adiabatic, the isothermal, this is true for all of it. For an isobolometric, what happens is this term is simply going to be 0 because the ratio of the volumes is 1, so this is going to be 0. Isothermal, this term is going to be 0 because it's constant temperature, so the ratio of the temperatures is equal to 1, so this is going to give me 0. Isobaric, there's nothing which is constant, so in that case, both of these two things will be changing. So this is satisfied for all of the different types of thermodynamic processes that we looked at. This is the most general thing. Good. So now that we have that, let's go ahead and do an example. So this says we want to expand 1 mole of a monatomic gas initially at a pressure of 5 kilopascals and a temperature of 10 Kelvin from its initial volume to a final volume. So let's write all of it. So we have 1 mole, so n is equal to 1 of a monatomic gas. Okay. We're going to take this thing from its initial pressure, so P initial, which is 5 kilopascals, and an initial volume, which is equal to 1 meter cubed, and an initial temperature, which is equal to 600 Kelvin. We're going to bring that thing to a final volume. So that final volume then is equal to 2 meters cubed. What we're also told is that here the pressure is related to the volume in the following way. So the pressure is a function of the volume, which is equal to 5 kilopascals times the exponential of the initial volume minus the final volume, all divided by some constant A, where A is equal to 1 meter cubed. So this says that actually the pressure exponentially changes as the volume is changing. That's what this thing is telling us. So good. So for here, we want to know, first of all, for part A, what's the final pressure? What's this guy equal to? Part B, we then want to know, what is the final temperature? What's this guy equal to? And then finally, part C, we want to know how much work is done during this expansion. So we want to know what is the work done by the gas in the expansion. And then finally, part D, we want to know what's the change in entropy. These are all the things that we want to know. So we want to know what's the final pressure, what is the pardon me, final temperature, what is the work which is being done, and then finally, what is the change in. Let's talk about all these beautiful things. Look at part A first. So to find the final pressure, all we have to do then is evaluate this final pressure at the final volume. That's it. So here, we know then that the final pressure is simply equal to the pressure evaluated at the final volume. So this is going to be equal to, I'm just going to call this P naught. That's the 5 kilopascals, and so on right now. Times E then to the plus initial volume minus the final volume, all divided by that quantity A. So this is going to be equal then to that P naught times E to the initial volume minus my final volume, but notice that my final volume is twice the initial volume, divided by that constant A. So, initial volume minus twice the initial volume is the same thing as negative the initial volume. And also notice that A here is also the same thing as the initial volume. So I can actually rewrite this guy as the initial volume as well. So this is going to be equal then to P naught times E to the minus B naught divided by B naught. Okay? So this guy is going to be equal to the initial, or P naught, times E to the minus 1, which is the same thing as P naught divided by E. Okay?
What does that say in the exponent?
Which one? This one? Yeah. That's minus the initial volume divided by the initial volume, because A is the same thing as the initial volume. Cool. Plug my numbers. This is what, 5 kilopascals divided by E. Anybody know what E to the 1 is? Anybody know what E is? What's that? 2.73-ish, somewhere around there. So I'm going to plug in those numbers. What I find in this case then is that the final pressure is 1.84 kilopascals. So this is my final pressure. Okay? Not too bad. So finally, we want to find, or not finally, but next, we want to find what is the final temperature. Well, what's happening here is this is still an ideal gas, which means that when it goes from the initial state to the final state, it has to be in an equilibrium state in the beginning, it has to be an equilibrium state in the final, which means that it has to satisfy the ideal gas law at both the initial and the final states. Which means that to find the temperature, all we have to do then is take the ratio of the two ideal gas laws at the two initial and final positions. Which means that I can take that the final pressure times the final volume divided by the initial pressure times the initial volume must be equal to the final temperature divided by the initial. This has to be true. What I know here again is that the final volume is related to the initial volume by simply twice. So this guy is actually twice the initial. And I know the final pressure here is simply actually equal to the initial pressure, the P0, divided by E. So what happened here is that the pressures will cancel, the volumes will cancel, which means this is going to be 2 divided by E, must then be equal to the ratio of the two temperatures, which means that the final temperature then must be equal to 2 divided by E times the initial temperature. Which tells me the temperature goes down. Initial temperature I know is 600, so I'm going to take 2 divided by about 2.73, which means this thing drops down to about 441.5 Kelvin. So this is my final temperature. All right. Not too bad. Part C, we now want to know what's the work. Now, here, obviously, from our definition here of the pressure, this thing depends on the volume, which means to find the work, we're going to have to integrate the pressure over the volume. So let's do that. Oh, did I change the temperature here? I was supposed to be changing entropy. Okay, sorry. Sorry. We'll get there in a second. So C, we know that's what? The work done by the gas is equal to the integral from the what? Initial volume to the final volume of the pressure integrated over the volume. Well, let's write that down. So let's insert our definition of pressures. So it's going to be equal to the integral from the initial volume to the final volume of the initial pressure e to the initial volume minus the volume divided by A, but A is the same thing as the initial volume, integrated over the volume. Now notice this thing here is actually the product of what? Two different exponentials. So I can always rewrite this then as what? The integral V0 to the final of the pressure e to the V0 divided by V0 times then e to the minus V divided by V0, all integrated over the volume. Okay with this? So all I'm using here, for anybody who might be confused, I'm using that x is equal, I have x raised to the a plus b power. That's the same thing as x raised to the a power times x raised to the b power. If I multiply those two together, I'm simply then summing the two exponents together. So here I'm doing the same thing. So notice here, V0 divided by Z0 is simply 1. So this is the initial pressure times E, which are both constants, times this thing, which is the only thing which actually has a volume inside of it. Which means these two are going to come outside of the integral, and then I'm going to simply integrate the exponential. So let's do that. So this says that the work done by the gas then is equal to the initial pressure times the exponential, times the integral from the initial volume to the final volume of e to the minus v divided by 0, v. Now, if I integrate an exponential, so let's say e to the ax dx, do you know what that is?
2x times a.
So this is equal to e to the ax, and am I multiplying by a or am I dividing by a? Divide. Good. So this is the same thing as 1 over a. Now, in this case, x is the same thing as v0. A then is going to be the negative, or sorry, x is going to be v, and then a is going to be negative 1 over v0. Which means the v0 is going to move to the top. So it's going to be the same thing as the initial pressure times the initial volume times the exponential, times then e to the minus v, sorry, I'm going to negative sign out here, divided by v0, evaluated from the initial to the final. Now, if I bring the negative sign inside, all that's going to do is switch the order of these two. We got to know the final volume is twice the size of him. So at the end of the day, what I'm going to get is, I'll roll this in. So this finally turns out to be E times the initial pressure times the initial volume times 1 minus e to the minus 2. So it's this guy. Plug in my numbers, what I find is this works out to be 3.16 kilojoules. So this is the amount of work that was done. Okay. Finally, for part D, we can now simply use this guy. So for part D, all I want to know then is what is my change in entropy going from the initial state to the final state. Okay. So for part D, we know that our change in entropy is equal to the number of moles times CV times the natural log of the ratio of the temperatures. So this is the final temperature divided by the initial temperature, plus the number of moles times the universal gas constant times the natural log of the final volume divided by the initial volume. We know the final volume is twice the size of the initial volume. We know the final temperature. All we have to do is simply put those in. This is monatomic gas, which means this is 3/2 times R So everything we find in this case is this works out to be 1.94 joules per Kelvin. So this is my change in entropy going from one state to another state. From my initial state to my final state. Right. A lot of integration this morning. It happens. Good. So let's continue talking about entropy. So historically, entropy first came about in the conversation of what's known as a heat engine and a refrigerator. So let's focus now on the heat engines and refrigerators. And we can redefine basically what the second law is in terms of these processes. So what a heat engine and a refrigerator are. So let's talk about these guys. So good. So what is a heat engine and what is a refrigerator? So basically what a heat engine is a heat engine takes disordered energy and uses that disordered energy to use it to a good use, which is to get some useful work out of it. So this is what a heat engine does. A refrigerator is basically the opposite. You try to take heat from a ordered state to then make it go to a disordered state, which is actually more complicated because you actually have to do work onto the system to actually do that. So in a heat engine, what it basically does is it takes a system through a cycle. Okay? So what has to be true then is that for a heat engine or a refrigerator, these are going to be cyclic processes. Meaning that when I plot it onto a PP diagram, I have to start off at one state, go through some sort of cyclic process, and then come back to this original state of A. Now, in this case, as we talked about before, any cyclic process, what has to be true then is that the change in internal energy for the entire cycle must then be equal to 0, which means then that the heat must then be equal to the work done by the gas. The work done by the gas then, in this case, is simply the area enclosed inside of the curve. So all of this here then is equal to the work done by the gas. So this is what has to be true about cyclic or heat engines. So we want it to be some sort of cyclic process. It's going to start at the same point, come back to that same point under some sort of process. So first let's talk about heat engines. So what's a heat engine? So yeah, what a heat engine does is it takes energy from a disordered state, uses that to then do work. So the way that this is going to work is we're going to have two reservoirs. The first reservoir is going to have a high temperature, which we're going to call T hot. The bottom reservoir is going to be our cold temperature, which is then going to be T cold. What we're going to do is we're going to use the fact that heat wants to flow from the hot source into the cold source. So we're going to look at the heat flowing from the hot source, use that onto some sort of mechanism to then get work out of it. So we're going to do some process here to try to get out work. And then whatever is left from our heat, we're going to dump that heat then back into the cold source. So this is going to be Q cold. Then to make this thing cyclic, we're simply going to connect these two guys back together. So in this case, we're going to take heat from the hot source, use that onto some mechanism to get work out of it. Whatever's left, we're going to dump it into the cold source, bring it back through to heat it back up into the hot source, and then make this guy a cyclic process. This is what we call a heat engine. This is your car. This is the way your car works. Your cold source, in this case, is the radiator. That cools it down, puts it back in. Life is great. What is a refrigerator? Refrigerator is basically the same idea. So again, I have my hot source here. I have my cold source here. I have T cold. We want to do basically the same idea. We want to be able to get draw heat, but in this case, we're going to do the opposite. What we want to do is draw heat from the cold source, take whatever's left and put that into the hot source. But it turns out that this doesn't happen naturally, so to get this guy to work, we have to actually do work onto the system instead. And to make it cyclic, we're simply going to connect these two reservoirs to each other. So we have a hot reservoir, we have a cold reservoir. In this case, we want to draw heat out of the cold reservoir to bring it to the hot reservoir. But to do that, it doesn't happen naturally, it doesn't happen spontaneously, so we have to do work onto the system to get this guy to work in this particular process. So these are heat engines and refrigerators. So from here, we can define some useful things. So the first thing we're going to look at is what's known as efficiency. So in a heat engine, so this is called heat engines, the efficiency of the heat engine then is going to be equal to what? The desired input minus the output. So let's see. So in this case, the output is the work. So in this case, we want to take the output, which is the work, divided by the input, which the input in this case is simply then equal to Q hot. So what we call efficiency, we're going to denote that by E, is then equal to the desired output divided by the desired input. The desired output in this case is we want to get work out of our system, and the desired input is we want to get this solely from the hot source or the heat coming from the reservoir. Now in this case, the work that this thing can do then is simply going to be equal to the difference between the heat going in versus the heat which is coming out. So this has to be equal to the work. So from here, the work then is going to be equal then to Q hot minus then Q cold. So if we plug this guy in, this says then that my efficiency then is going to be Q hot minus Q cold divided by Q hot, which is the same thing as 1 minus Q cold divided by Q hot. So this is what we call the efficiency. So the efficiency then of our heat engine is 1 minus the ratio of the cold heat divided by the hot heat. Now, typically what's going to be happening is the cold heat then is the heat which is moving out of the system. This is the heat which is moving into the system, which means that this guy is technically negative by its definition, so we're going to put absolute values on it. Just to make sure that he is actually positive. Refrigerators, we're going to define something similar, but this is what's known as the coefficient of performance. So the coefficient of performance, we're going to call that COP, is equal to basically the same kind of idea. So this guy is equal then to the desired output, which is called hot, or called QC, there we go, cold heat, divided by the desired input, which in this case is simply the work. So that's what we call the coefficient of performance. So it's the cold heat divided by the work. Okay, just the desired outputs divided by the desired inputs. So using heat engines and refrigerators, we can now write down some new definitions of the second law of thermodynamics. So historically, the second law of thermodynamics then came from, again, looking at heat engines. And each one of these different heat engines has these different definitions. So according to PHYS, what PHYS said was that the second law says that heat never flows spontaneously from a colder body to a hotter body. So the fact that we have to do work onto the refrigerator to draw heat from the cold source into the hot source, where in this case, we can actually use the heat flowing from the hot source into the cold source to get work out of it, means that it's actually spontaneous for the hot to go into the cold, but not vice versa. So Clausius' definition then of the second law says that heat never spontaneously flows from a cold source to a hot source. So this is the second law of thermodynamics based off of PHYS205. So based off of these heat engines, again, the observation that we can get work out of an engine by having heat flow from the hot source to the cold source, but we have to do work in the opposite direction to get heat to flow from the cold source to a hot source, means that heat will never spontaneously flow from the cold to the hot. The only way to get it to do so is we have to do work onto the system to do that. Another, by Lord Kelvin and Max Planck, says that no heat engine operating in a cycle can absorb energy from a reservoir and use it entirely for a performance of equal amounts of work. So I'll write that down. So this says no heat engine operating in a cycle can absorb energy from a reservoir and use it entirely to do work. What does that mean? So basically this comes back to the idea of efficiency. So from efficiency, what we said was that efficiency is equal to 1 minus Q cold divided by Q hot, right? This is how efficient that my engine is. So what this statement is basically saying is it's saying that the second law actually says that the efficiency can never be equal to 100%. Because I can never draw all of the heat from a hot source to do work onto it. I have to have some amount left over to put back into the cold source, i.e. the cold heat, the heat flowing out of the system to make this into a cyclic process. Okay? So what Kelvin's and Planck's version of the second law then says is that the efficiency must always be less than 100%. I can never, ever, ever build an engine which is equal to 100% efficiency. This is the second law. So in terms of heat engines, again, historically, which came first before the idea of disorder, which was brought up by Boltzmann, these are the natural definitions of the second law. So again, heat never spontaneously flows from a cold source to a hot source, and in a heat engine, I can never have something which is 100% efficient. That then begs the question, which is what we're going to talk about on Monday. If I could never have a heat engine with 100% efficiency, what then is the maximum amount of efficiency that I can have? So this is the question we're going to ask on Monday. So on Monday, we're going to ask, what is the greatest amount of efficiency that my engine can actually obtain? And then even then, all realistic engines will have less efficiency than this engine. This will be a purely theoretical engine, which we cannot build in nature. So all efficiencies must be less than this particular efficiency. This is what's known as the Carnot engine. So we'll talk about the Carnot engine on Monday. After we do that, we'll be done. Life will be great. We'll do an example using all this stuff. We'll do some group exercises and stuff on Monday. Wednesday, then, we'll review for the thermo parts of the exam. Remember, the final is going to be half thermo, half cumulative. So Wednesday, then we'll review for that guy, and then I guess on Thursday, we'll review for the cumulative parts, and then Friday, we just won't. Give you a nice extra day off before finals. So I'll see everybody on Monday. Oh, sorry.
Do you know what time the final is? Because I know
It's from 9 to 11. Yeah, it's supposed to be in this room 9 to 11 on the very last day of finals, just to make our life much more. So 1 week from, or 2 weeks from today. Is our final. So May 7th. All right. I'll see everybody on Monday. Have a good weekend. Get some sleep. And
I would suggest